I'm Cadet Anika Ganesh.
I'm Cadet Schleck.
I'm Cadet Langou.
And today we will be presenting on determining the effect of observing aggressive behavior on the actions of infants.
Now for some background.
Our model and problem are based on a study that we found detailing how a special subgroup of infants are more likely to punish aggressive behavior that they observe in others.
The bad population shows aggressive behavior, and the good population stops this behavior.
This has implications in society because they carry these behaviors into adulthood.
Due to the interactions between the subgroups, these behaviors can also lead to fluctuations in the subgroup populations, especially decreases in the what we call bad population overall. We are proposing a model where we see the changes in population of infants who are inclined to punish aggressive behavior, infants with aggressive behavior, and neutral populations of infants.
The inspiration we'll use for this model is the competitive Volterra model to see population change over time. This competition model is usually used to see animals in their natural habitat. In this model, we'll be looking at the good children who punish the bad behavior of the bad children. And they will be competing against each other and to get the neutral populations to join their groups.
Our first assumption is that the number of people in our population don't change. The subgroups do, but the total doesn't. Our second assumption is that the likeliness to act is shared by a certain group of infants. This is the subgroup that punishes aggressive behavior in other infants. And then our third assumption is that any individual can switch into another group at any time. So that can be from one level of good to another level of good, or from bad to neutral, etc.
So our variables for the first transform are t, time since interaction began, b of t, the number of bad infants at time t, which the bad infants are the aggressors, g1 of t, the number of good infants in group 1 at time t, which those are the infants who punish the other infants, and n of t, the number of neutral infants at time t, which they are the victims of the aggressive action. Our parameters for the equations are R1 is the number of individuals from the neutral population that became part of the bad population over time, K1 is the carrying capacity of the bad population, Alpha 11 is the effectiveness of the bad population in turning the neutral population to bad, and Alpha 12 is the effectiveness of the bad population in turning the good population to bad. Our parameters for the second equation are similar to that of the first equation, except instead of for the bad population, they are for the good population.
Equations. The rate of change of the bad population is equal to the growth rate of the bad population times the quantity of 1 minus how much the bad population affects the bad population plus how much the good population affects the bad population, all over the carrying capacity of the bad population. At time t equals 0, there are 400 people in the bad population and 500 in the good population. At any given time t, our neutral population is equal to the total population, which is 1,750, minus the amount of people in the bad population at that time, plus the number of good people in the population at that time.
For our first transform, we have the x-axis in time and days, and the y-axis in number of people in the population. This model always adds up to 2,000. And that is because the neutral population fluctuates with accordance to the good and the bad population. The good population wins over the bad population in this model.
So now we will complicate our model. We will add 2 more populations of good infants, good 2 and good 3, and this will make our competitive Volterra model more interesting in order to predict the species outcomes according to the competitive relationships between 5 species. Our variables and parameters will follow, so there's no need to redefine them at the moment.
Equations. So our new system of equations is the same format as our original system. The only difference is that there are 2 new variables, which are G2 and G3, which are other subsets of the good population that are not quite as severe or strong as the G1 population. So as such, we have new initial values for those populations, and a new equation to model the amount of neutral people in that population. So these are our new parameters, and again, it's in line with our original parameters. The only difference is that we have 2 new good populations. So as such, the growth rates are affected, but the constants of change are still the same, still zero point 0.1, and the carrying capacity is the same across the board for every subgroup population, remains at 500.
In front of you is the model for our adjusted transform. As you can see, the differing alpha values in our parameters on the last slide create very interesting effects on the 5 respective populations. So our good 1 population decreases greatly. Our bad population decreases a significant amount as well. Our neutral population decreases, and our good 2 and good 3 values increase greatly, which is the result of our alpha parameters as stated on the last slide.
For our parameters, we have our growth rates all equal to 0.1 and our carrying capacities all equal to 500. All our alphas, 1 and n, are different because this is how the different populations will affect each other.
So for our different parameters, things that have changed we've highlighted in red and gray. So we've changed R3 to 0.15 from 0.1 for our G2 population, and as well as alpha 31 and alpha 41 have changed as well, and alpha 23 and alpha 12. The carrying capacity for each population has remained the same.
With this new different adjusted transform, we get that the good 2 population ends up on top with the most people at the end of the 300 days, and followed by good 3, then the neutral population, then the good 1, and the bad population. So overall, the good populations have won against the bad population.
These adjusted transforms have allowed us to make conclusions based on the aggressiveness of different groups of infants. So in the long term, we believe that G3 will become the largest population, which G3 is the most good population, meaning that they punish the bad population in the most severe way. If this subgroup does really exist, they do have the potential to create positive impacts on our society because they convince others, the bad infants or the neutral infants, to join their population and in turn practice this morally correct behavior of stopping aggressive behavior. So the most aggressive punishers, the G3 group, as we saw according to our alpha parameters, in our society have the greatest positive impact and will eventually outnumber all of the other populations. So over time, in the long run, they will, by their actions, convince others to join their subgroup population and eventually will greatly outnumber the other populations.
Now we'd like to take a minute to discuss the implications of our model. So the most important implication is that within time, our society will get better and better as a result of these interactions. So when good people in the G1, G2, and G3 populations correct aggressive behavior that they observe in the bad population, the number of bad people will decrease and go to neutral, and then those neutral people have the potential to become good, either G1, G2, or G3. So overall, these interactions are bettering our society by decreasing the number of bad people. Also, bystanders and those unwilling to take a strong stance will eventually die out. As we've seen, the G1 population goes to 0. So G2 and G3 are the ones that emerge because they are the most aggressive of the good population. So with time, society will be filled with people who are either extremely aggressive or extremely aggressive in a positive way. This may increase the amount of friction and conflict that we see in society because those two groups will not mesh, and it might increase the amount of violence as well because we won't have moderate or neutral people in our society to regulate. But that's just an implication that we have to accept with this model.
If we had more time given, our possible improvements would be to look at more data so that we can find better parameters that are true to real life. We could have created more bad populations so there weren't 3 good populations and only 1 bad population to see how the different levels of aggressiveness lead to the long-term behavior of the populations. and we would have done more research on how it not only affects infants, but maybe the adult population. And we would have wanted to look at our own data in the adult population to see how it affects us in society.